So in order to convert a true heading into magnetic heading, you need to know the value of variation. And this variation value can be figured out from the sectional chart, VFR sectional chart that you will use for your cross country flights. Now when you look at this chart closely, you will find one red color. You may not be able to see it, but there is a red color dash line here. There is a red color dash line, something like this. Okay, so all your VFR sectional charts will have this red color dash lines. This red color dash lines are nothing but isogonal lines. Just like VFR sectional charts, your IFR low altitude onto charts will also have this isogonal lines. And there will be a number next to this isogonal line. Now in this case, the number is some 10 degree east. Some 10 degree east value is written here. Okay, so if you're flying in this particular region, you're going to use this value of variation for your calculations. Okay, so whatever your true heading, let's say it's 120, so you're going to use the variation of 10 degree east. So your magnetic heading or magnetic course will be 110, it will be least. Okay, so in order to convert true heading into compass heading, a compass card and a map with isogonal lines depicted will be required. Question 62. If tailwind increases, distance to critical point will what? Will it decrease? Will it increase? Will it remain the same? So let's say this is your point A. This is your point B. Okay, you're flying from A to B. This is your critical point. Okay. This is there are calm conditions right now. Okay. And the critical point is right in the center between point A and B. Now, when the wind starts blowing, the critical point will tend to blow or will tend to move in the direction of the wind. So let's say the calm winds terminate, the calm atmosphere is no longer there, and winds start blowing from the front, from the destination. Okay, that means going from Alpha to Bravo, you're getting a direct headwind. So what will happen to your critical point position? Initially, the critical point was right in the center of this route. But when the headwind starts blowing, the critical point will tend to move in the headwind, into the headwind. So the critical point will move from here to somewhere here. So the new position of the critical point will be somewhere here into the wind. If the wind shifts, okay, if the direction of the winds of this wind shifts and it becomes tailwind now, so what will happen to the critical point? The critical point will move again into the wind. So the new position of the critical point will be somewhere here near the departure aerodrome. Okay, so if wind is blowing from this direction, the critical point will tend to move into the wind. If the wind is moving from this direction, the critical point will move into that direction, okay, or into that wind direction. So in this case, wind tailwind increases. That means you were getting tailwind, you were receiving tailwinds initially, but now the magnitude or the strength of the tailwind has increased even more. So what will happen to the critical point? So since you are getting tailwinds, critical point will be near your departure airport. And now, as a second condition, when the wind strength of this tailwind increases, the critical point will move further towards the departure airport. Okay, even more inside. So the distance to CP will decrease. So what will happen? As the critical point moves towards your departure airport, the distance between your departure airport and the critical point goes on decreasing. Okay, so what happens to the distance to your critical point? It will decrease. In the matter of headwinds, what will happen to the distance to critical point? The distance to critical point will go on increasing. Okay, so read the question carefully and understand this important property. Next, pressure altitude is 5,000 feet. QNH is 1018.25. What is the indicated altitude? So let's say this is your airport. Okay, this is your airport. And QNH is 1018. So QNH is 1018. Standard pressure setting is 1013. The pressure altitude of this airport will be measured from, correction, it will be measured from standard pressure setting 1013, and pressure altitude here is equal to 5000 feet. NH1018, what will be altitude indicated? In order to get altitude indication, you will have to put QNH value in your altimeter setting window. So altitude will be measured from QNH datum. So this altitude is made up of two parts. It is made up of this pressure altitude part, this part pressure altitude, plus this additional part which is the height difference between these two pressure levels, right? So what is the difference between these two pressure levels? It is 1018 minus 1013, 5 millibars. So that will be equal to a height difference of 5 into 30, where 1 millibar equals to approximately 30 feet, so 150 feet. So this height difference is equal to 150 feet. Pressure altitude we know is 5000. So total altitude will be pressure altitude plus height difference, 5000 plus 150. So altitude will be 5150 feet. 5150 feet. Okay, so this is your answer. Next. Earth's atmosphere causes signal delay as global navigation satellite signals pass through it. The most prominent error responsible for delay is multipath error, ionospheric delay error, tropospheric delay. So correct answer is, the most prominent error is tropospheric delay. So we will look at tropospheric delay as it relates to GPS antenna. Tropospheric delay refers to satellite signals slowing down. So very important word, slowing down as they pass through the troposphere, the lowest layer of Earth's atmosphere. This delay impacts the signal timing accuracy that GPS devices rely on to determine precise locations. Understanding tropospheric delay is crucial for anyone using or developing technologies requiring high positioning and timing precision. The troposphere, unlike higher layers of the atmosphere, contains a variable amount of water vapor, which significantly contributes to the slowing of the signal. So this is the main cause or reason. Because of this variation, the extent of the delay can fluctuate based on the weather, location, and time of day, introducing challenges in compensating for these changes. Professionals in fields such as geolocation services, survey, meteorology depend on accurate GPS data for critical applications. They use sophisticated models, algorithms to predict and adjust for tropospheric delay effect, enhancing reliability and accuracy of the data received. Okay, for instance, in weather forecasting, accurate measurements of the troposphere are essential for predicting storm movements and understanding climate patterns. Additionally, tropospheric delay is a critical factor to consider in design and optimization of GPS antennae. These antennae need to be highly sensitive and capable of compensating for or minimizing the effects of such delays to ensure integrity of location data. Engineers, designers work tirelessly to improve antenna designs to mitigate the impacts of troposphere delay, employing advanced materials and innovative configurations. As our reliance on GPS technology grows, so does the importance of addressing the challenge posed by tropospheric delay. From enabling autonomous vehicles to navigating city streets safely to ensuring accurate timing for global financial transactions, the ability to effectively deal with phenomenon is key to continuing advancement and expansion of GPS. So basically factors influencing tropospheric delay are high humidity and temperature and pressure changes. Okay, so then here they have given the techniques used to mitigate these effects of tropospheric delay. You need not know everything by heart, but just remember this first introductory part. Okay, tropospheric delay causes slowing down of signals. Tropospheric delay is a cause of or is caused by humidity in atmosphere. Okay, so tropospheric delay. Next, satellites used in global navigation satellite system orbit the Earth once in 12 hours, once in 8 hours, once every 24 hours. So very important. Satellite orbit. These satellites are located 20,200 kilometers above the ground. They can make a revolution around the Earth in 12 hours. That means one revolution takes 12 hours. That means in a day of 24 hours, they will make two complete revolutions. Any location of the Earth is always within the range of a minimum of 6 satellites. Satellites cannot access systems that are on the other side of the planet. As of today, there are 31 of these satellites functioning and orbiting a planet. A 32nd satellite is in the orbit but has a malfunction. So the correct answer here is satellites orbit the Earth once in 12 hours. Very important. Lines joining places of zero variation are called isogonals, isoclinal, ergonic lines. So ergonic lines are lines of zero variation. Lines of equal variation value, any variation value other than zero, are called isogonal lines. Next, 67. Primary radar detection is based on detection. Primary radar detection is based on dash and and secondary radar is based on what detection. Okay, so remember, primary surveillance radar. Let's say this is your primary surveillance radar on the ground. Okay, primary surveillance radar on the ground. Here is your traffic aircraft in the atmosphere. Here is your traffic aircraft in the atmosphere. Now, what will this primary surveillance radar do? This primary surveillance radar will transmit a radio signal in the direction of this traffic aircraft. This radio signal will go to that aircraft, strike that aircraft, and come back to your primary surveillance radar. It will come back to your primary surveillance radar. Okay. So this is called echo principle. Echo is nothing but reflection. So whatever radio pulse or radio wave that you are sending towards that aircraft, it will go to that aircraft, strike it, and bounce back. So all this operation, all the primary surveillance radar operation happens on one fixed frequency f. So the transmitted frequency will be equal to the reception frequency. Now secondary surveillance radar, let's say this is your ground surface. This is your ground surface and this is your secondary surveillance radar equipment. There is aircraft in the air. Now what will happen? In case of secondary radar, this ground radar antenna will transmit a wave, a radio pulse, in the direction of this aircraft, let's say. This radio signal will be called interrogation, interrogation signal, and it will be transmitted on a frequency of 1030 megahertz. 1030 megahertz. The transponder equipment in your aircraft will reply to this interrogation wave by sending another signal down to that radar, and this signal will be called reply signal, and it will be transmitted on a frequency of 1090 megahertz. Okay, so this is the concept of secondary surveillance radar. The transmitted frequency 1030 will be different from the reception frequency 1090 megahertz. Okay, so this is the main difference between primary radar and secondary radar. Primary radar uses echo principle. Secondary radar uses transponder, a specific airborne equipment Okay, transponder can also be located on the ground. So basically, secondary radar will use a specific responding equipment called transponder to get a reply pulse. This reply pulse will have its own energy. Interrogation signal will have its own energy. The reply pulse will have its own different energy. But in case of primary radar, the same frequency is used throughout the operation. So that's why the energy of the transmitted wave will be equal to the energy of the reflected wave. So primary radar detection is based on signal reflection echo, transponder response, interrogator signals on board. So it is signal reflection echo. And secondary radar is based on transponder response. Yes. So option A will be the right option. Flight level 250 outside temperature -15, task 40, 450, calculate local speed of sound. Now local speed of sound equals to 39.17 square root of temperature in Kelvin. Now what is outside air temperature -15 degrees Celsius in terms of Kelvin? It will be -15 plus 273, that is 258. So 39.17 square root of 258. So 258 square root into 39.17 is 629 knots. Now calculate Mach number, which is true airspeed divided by local speed of sound. So 450 divided by 629 is equal to 0.7. Simple. Next. Code with specific meaning, no code allocated or in exiting FIR is what? 000, 2000, 7000. So what transponder code should you set? If there is no specific transponder code allotted to you, or if you're flying in a particular airspace where no transponder equipment is required, so what transponder code would you enter in that equipment? So remember all these important transponder codes. So 000 is the transponder code for military intercept. Okay, so that is very important. Now 1200 is the transponder code when you are flying BFR, and this is the standard SCOC code in North American airspace. 2000 is SCOC code when entering a secondary surveillance area from a non-secondary surveillance area. That means you're flying from an airspace where transponder is not mandated into an airspace where transponder is required. So if you're flying from such an area, okay, your transponder code should be set to a code of 2000. Okay, so the correct answer here will be 2000. Next. 7000 is VFR standard SCOC code when no other code has been assigned. Okay, so in some countries 7000 can also be put for VFR. In America 1200 is used. 7500 unlawful interference, 7600 lost communications, 7700 emergency, 7777 is again military interception. Okay, next, last question. If the pulse width or length in a primary radar is so and so, zero point 0.5 microseconds, range resolution will be what? Now, pulse width determines your range resolution. Your beam width determines your azimuth resolution. So, range resolution, which is determined by your pulse width, is equal to speed of light speed of radio waves multiplied by the pulse width given to you divided by 2. So 3 into 10 raised to 8 meter per second into pulse width of zero point 0.5 microseconds, so 10 raised to minus 6 seconds divided by 2. So 10 raised to 2. So 1.5 divided by 2 is 0.75 into 10 raised to 2 meters. So 75 meter. So range resolution equals to 75 meter. Option Charlie. Remember the formula. Okay. Speed of light into pulse width divided by 2. So this concludes the lecture. I hope